This video will cover section 6.2 on energy changes in reactions. So, to break a bond requires energy because atoms are more stable when they are bonded together. And so when you separate them, they will be less stable, and so it will require energy to break bonds. And so on the other hand, forming bonds will release energy because it stabilizes the atoms to be bonded together. So let's take, for example, two chloride or two chlorine atoms, and if they are bonded together in the molecule Cl2, and so to cleave this Cl-Cl bond, you will need to provide 58 kilocalories per mole to break the bond. And so this is called an endothermic process because you need to add energy to the molecule to be able to break the bond. And delta H here is the energy absorbed or released in a reaction, and it is called the heat of reaction or the enthalpy change. So enthalpy change is symbolized by delta H, but it's also called the heat of reaction. And so that heat of reaction, in the case where you want to cleave the bond between the two chlorine atoms, it will be a positive value because you need to provide that amount of energy of 58 kilocalories per mole. So when it's endothermic, it's positive. Now, if we have already this no, let's say we start with single atoms, single chlorine atoms, and we want to form the Cl-Cl bond. Then in this case, when we form the bond from the two single atoms, energy will be released to the surrounding, and 58 kilocalories per mole will be released. So notice how it's the same number, but the delta H this time is negative because this is released to the outside. It's exothermic. Energy is released to the outside or exiting the system. And the system here was the two chloride atoms or the two chlorine atoms that we are binding now together. And when we're binding them, energy is released. So you want to remember this fact that when you're breaking bonds, it requires energy. When you're forming bonds, it releases energy. And so this table is pretty important. You want to keep a mental picture of this page. So it summarizes what it means to have an exothermic reaction and an endothermic reaction. So let's look at the left side first. When you have an endothermic reaction, endothermic means you need to absorb heat. So heat is absorbed by the system you're looking at. And so the delta H will be positive. You need to provide that energy for the reaction to occur. And you have endothermic reactions when the bonds broken in the reactant are stronger than the bonds formed in the product. So you're breaking stronger bonds than the bonds you are forming. So that's why you're requiring more energy for this to happen. And so in chemistry and when we are talking about energy, what you need to remember is that the lower the level of energy and the more stable your substance is or your chemical species. And so here, when we have the reactant with a lower energy and we end up with products with a higher energy, that difference of energy between the reactant and the product will have to be provided from the outside. And so that's why it's an endothermic reaction, because you need to provide that energy symbolized by delta H, and it's a positive value. You need to provide that to the reactant so that they become the product and they will have a higher level of energy as products. So you want to remember that it's this case. So you have reactant at a lower level of energy and you end up with product at a higher level of energy. And that's because the bonds in the reactant are stronger than the bonds in the product. Now, if we look at the case of an exothermic reaction, exothermic means that heat is released to the outside. Heat is exiting the system you're looking at. So the delta H will be a negative value. And so in this case, the reactants are higher in energy than the product. They have more energy, and the bonds in the reactant are weaker than the bonds in the product. So the bonds formed in the product are stronger than the bonds in the reactant, and so the product are more stable, and so they will be lower in energy. And so you start with higher energy reactant, end up with lower energy product, which are more stable. And so the difference in energy between the two is released to the outside. And that's why it's an exothermic reaction. And so you have to remember that then the delta H is a negative value. So let's use this knowledge and go through a learning check. Given the following equation, chemical equation, CH4 in the gas phase plus 2 oxygen molecules in their gas phase will give CO2 gaseous and 2 molecules of water liquid. And so we are given the delta H for this reaction. So delta H, remember, is called the heat of reaction or the enthalpy change, and it's negative 213 kilocalories per mole when you have this reaction occurring from left to right. So answer the following questions. Is heat absorbed or released? So the key to find the answer to this question is to look at the delta H, and if it's a negative value, that means it's a exothermic reaction and heat will be released. So here heat is released. Which bonds are stronger, those in the reactant or those in the product? So when heat is released, that means you will have product lower in energy than the reactant, and so their bonds will be stronger, because in chemistry, whenever you have a lower energy product, it means it's more stable, it has stronger bonds. So the bonds in the product will be stronger. So are the reactant or product lower in energy? And so here, because product have stronger bonds, they will be lower in energy than the reactant, right? So we start with high energy reactant and we end up with low energy product. And so the difference in energy is released to the outside. So it's an exothermic reaction. So it's very important to know this, the link between the negative value of the enthalpy and the fact that it's an exothermic reaction. Let's look at another example. It's a different reaction here. So 6 molecules of carbon dioxide in their gaseous state plus 6 molecules of water in their liquid state combine to make C6H12O6 aqueous, which is a glucose, plus 6 molecules of oxygen in their gas phase. And delta H, the enthalpy change or the heat of reaction, is positive 678 kilocalories per mole. So so here, is heat absorbed or released? So when you have a positive enthalpy, positive heat of reaction, heat is released. Heat is absorbed by the reactant. So heat is absorbed by the reactant, and the amount is given by this value. 678 kilocalories per mole are necessary for this reaction to occur. So which bonds are stronger, those in the reactant or those in the product? So if you need to provide this energy, that means your product will have more energy than the reactant, right? So you will end up with product with higher energy, which means weaker bonds. So the bonds in the reactant are stronger because you need a lot of energy to break them. So are the reactant or product lower in energy? And so here, when you have reactant with strong bonds that you need to break and then provide energy for this, that tells you the reactant are lower in energy than the product, because you provide energy that will be then incorporated into the products. So products will be higher in energy. So is the reaction endothermic or exothermic? And here it's endothermic because it's a positive enthalpy change or a positive heat of reaction. So I wanted to emphasize that the previous equation here that we had, and back to the previous slide where we had methane plus oxygen give carbon dioxide and water. And here the heat of reaction was negative and it was an exothermic reaction. I hope you also recognize that this is a combustion reaction when you have a compound made of carbon and hydrogen being burned in oxygen produces carbon dioxide and water. This is a typical combustion reaction. And we know that when we are doing combustion reaction, there's a lot of heat released, right? And that's why we actually use those combustion reactions. It's to take the energy from them. This is natural gas here. When you are burning natural gas, you're producing carbon dioxide and water and getting a lot of heat in exchange, right? So that's why this confirms also that it's an exothermic reaction. This reaction here looks like it's the reverse process. It's actually respiratory it's the inverse of, sorry, it's the photosynthesis here. When you have carbon dioxide and water combining together and making glucose and oxygen, this is what the photosynthesis is doing to produce the energy for plants. And so you're taking carbon dioxide and water from the atmosphere and from the roots of plants, and then they're producing glucose and oxygen. And so this is very endothermic, as we decided here. It's endothermic because you need the UV light for this reaction to occur. So UV light will provide the energy needed for this reaction to occur. So let's look at yet another type of reaction here. Given the following equation about the fermentation of glucose to ethanol and CO2 and the delta H value. So here C6H12O6 is glucose. Glucose can be fermented into ethanol and carbon dioxide. This is the heat of reaction is negative 16 kilocalories per mole. So this is an exothermic reaction here. So how many kilocalories of energy are released from 1 mole of glucose? So we'll look at that first question first. How many kilocalories of energy are released from 1 mole of glucose? And so what we didn't say earlier is that when you have the heat of reaction, negative 16 kilocalories per mole, and it's associated with a chemical equation like that. It means for the chemical equation as it is written, per mole of reactant here, so per mole of C6H12O6, you will make 2 moles of ethanol and 2 moles of carbon dioxide. And so you will release 16 kilocalories when you have these proportions reacting and you know, this amount of product being produced. So that means when 1 mole of glucose is reacting and fermenting, you are releasing 16 kilocalories to the outside. So that's what this means. The delta H equals negative 16 kilocalories per mole means that 16 kilocalories are released when 1 mole of glucose is fermented. So let's look at question B using the same information. How many kilocalories of energy are released from 6 moles of glucose? So this time it's not 1 mole of glucose that reacts, but 6 moles of glucose. So again, the delta H that was given here means that it's releasing 16 kilocalories when 1 mole of glucose is fermented. So now we need to scale up to 6 moles. And so this negative 16 kilocalories per mole can be used as a coefficient or conversion factor, because that's an equality. It says that when 1 mole of glucose is fermented, you're releasing 16 kilocalories. So it can be seen as an equality and a conversion factor. And here the given amount would be 6 moles of glucose. So you start with 6 moles of glucose and you will multiply by the fact that you release 16 kilocalories per mole of glucose. And so by writing it this way, we see that the moles of glucose cancel and that you are multiplying 6 by 16 and you get negative 96 kilocalories, because the negative sign here reminds us that this is released to the outside because it's an exothermic reaction. So 96 kilocalories are released when 6 moles of glucose are fermented. And so let's look at question C now. How many kilocalories of energy are released when 1 mole of ethanol is formed? So this time we are not looking at mole of glucose that gets fermented, but we are looking at moles of ethanol that is being formed. And here it's asking how many kilocalories of energy are released when only one mole of ethanol is formed. But the information we have here, the 16 kilocalories per mole, means that 16 kilocalories are released when 1 mole of glucose is fermented and when 2 moles of ethanol are produced, right? It goes with this equation as it is, and here we have 2 moles of ethanol being produced per mole of glucose being fermented. So that means we will use the equality that says 16 kilocalories released per 2 moles of ethanol, right? It's now we need to focus on ethanol, and so we have this amount of energy, but when we have produced 2 moles of ethanol. So now if we take the amount, the given amount in the question, it's 1 mole of ethanol. So then if you take 1 mole of ethanol and then multiply by the conversion factor that says now that it's negative 16 kilocalories released per 2 mole of ethanol, by multiplying that by 1 mole of ethanol, the given amount, we see that the moles of ethanol cancel, and we do 1 times negative 16 divided by 2, and it's negative 8.0 kilocalories that are being released when only 1 mole of ethanol is produced. So 8 kilocalories are released when 1 mole of ethanol is produced, which means half of the energy is released because you're producing only half of what the equation tells you that is produced.